Hello everyone and welcome to today's session, How Web Protocol Weaknesses Enable Layer 7 DoS Attacks. I am Shilpa Sharma and I will be your host for the day. Before we get started, we would like to go over a few house rules. For our attendees, the session will be in listen-only mode and will last for an hour, out of which last 15 minutes will be dedicated to Q&A. Our speaker for today's session, Michał Sołtysik. Michał is a deep packet inspection analyst and cybersecurity consultant specializing in network edge profiling and zero-day attacks. With a focus on IT, OT, and IoT areas, he has identified around 254 protocols used for cyber attacks. Michał is also a skilled digital and network forensics examiner, a cyber warfare organizer, and a SOC trainer, enhancing his cybersecurity roles with a broad range of expert knowledge. Without any further delay, I would hand over the session to you, Michał.
Thank you so much for the introduction. Hello, everybody. Thank you so much for joining me, and thank you, EC Council, for having me. Okay, so today's webinar topic is how web protocol weaknesses enable layer 7 DOS attacks. You can find out about me if you want to get to know more about me on my official website. Just go to michalsołtysik.com. I currently hold over 30 certifications from most of the leading authorities in accredited education, training, and certifications for cybersecurity professionals. Okay, so let's start. In this session, we'll explore why modern protocols like TLS 1.3 still leave web pages vulnerable to layer 7 DOS attacks. We'll take a closer look at protocols such as ICP, DTLS, WTLS, QUIC, and QUIC, and discuss how the design can be exploited. Before we dig deeper, let's clarify what layer 7 DOS attacks are. These attacks can't rely on flooding the networks. They exploit application logic, that's the key, like HTTP, to drain server CPU and memory with requests that seem legitimate, often causing disruption without high traffic volume. Layer 7 DOS attacks are particularly dangerous because they look like normal user behavior, yet they exhaust critical server resources like CPU and memory. These are, in the slide, you can see quite a few characteristics, so you can check them out in more detail later once you can get access to this webinar later on. Layer 7 DOS attacks are particularly dangerous, as I said before, and this affects quite a few protocols. Now let's start with the first protocol. The Internet Cache Protocol, or ICP, was designed to let web caches talk to each other and reduce redundant requests to origin servers. I will not get into more details. You can check this out a little bit later as well. There are quite a few security risks, though, when it comes to this particular protocol. So the ICP OP head object operation can bypass standard security checks like authentication or age validation for HTTP. This creates opportunities for attackers to access sensitive data directly from cache without ever triggering normal security mechanisms. Another one, when ICP messages exceed the MTU, they get fragmented over UDP, and that opens the door to DOS risks. These fragments burden the server with reassembly, and when abused, let attackers exhaust server resources without high bandwidth, making the attack efficient and stealthy. Because ICP can bypass HTTP validation, as I said before, attackers can poison the cache with malicious content. When it comes to all these security risks, in the slides that you can check out later, you can also see some scenarios that can kind of make you get familiarized with such scenarios, exploiting these weaknesses in more detail later on. I had the chance to speak to Peter Danzig, the creator of ICP, and he was very clear in his view that ICP is essentially a historic relic. He told me directly when we spoke that HTTP 1.1 made ICP redundant, and that while it was once, I quote now, a cute idea, end of quote, it holds little value today. According to him, it wouldn't really be used in any meaningful way these days. So the question should be now, is it still being used? I mean ICP. Technically, yes, but mostly for backward capability in legacy systems, like older QUIC deployments, for example. In practice, it's considered obsolete in modern environments, where more secure and efficient protocols like HTTP 1.1, for example, have taken over. Although Peter Danzig considers ICP obsolete, and I guess that most of you have not heard too much about this protocol, the reality is a bit more complex. Some legacy setups, especially older QUIC deployments, still supported for backward capability. And this causes, as a result, a possibility for exploitation for the attackers. Now, this network dump shows that before launching various DOS attacks simultaneously, an RTT baseline was established using ICMP. And 2 minutes later, ICP was used to measure RTT for comparison. So in this very case, we just see two different protocols, both used for the same reason, that is RTT measurement. And based on the responses, an attacker can see whether or not more traffic should be generated and sent over to the target so that the DOS is more successful. This network dump, though, proves that ICP can be used for constant RTT measurement. I emphasize constant. Each packet provides data to the attacker. In Wireshark, in the packet details pane, not visible in the screenshot though, the use of a specific ICP opcodes and/or options would determine whether or not the traffic was generated to measure the RTT. Now the second protocol, WTLS, or Wireless Transport Layer Security, was designed to bring encryption and integrity to mobile networks through the wireless application protocol. It's based on TLS 1.0, and this is the very root cause of which this protocol is also vulnerable to some attacks. Okay, so WTLS handshake process is designed to securely negotiate encryption and authentication settings between the client and server. It includes steps like exchanging cryptographic parameters, verifying certificates, setting out encryption keys, and finishing with mutual confirmation to ensure the handshake wasn't tampered with. Yet again, more information can be obtained once you check out this presentation in more detail later on. Okay, let's move on. The change cipher spec phase marked the transition to encrypted communication, making it a critical point in the handshake. But it's also a potential attack surface, which is very critical. If abused, attackers can trigger repeated cryptographic operations, draining several resources and enabling a form of layer 7 DOS. So basically, this is where the vulnerability lies in. This is where the vulnerability becomes a weapon. By sending multiple change cipherspec messages, an attacker can overload the server with expensive cryptographic operations. Now let's take a look at some examples. I have 3 examples to show you. In the first slide, we see 2 of them. So these examples of WTLS change cipherspec messages show attempts at resource exhaustion. As you can see, this traffic was generated from public IP addresses hosted in China and India. And this is the third example. As you can see, we have quite a few packets, very same ones, trying to do exactly the same thing. Okay, now yet another protocol, DTLS. So it's essentially TLS adopted for UDP. It brings encryption, authentication, integrity to datagram-based communication. It's used in latency-sensitive apps like VoIP, VPNs, and IoT, and it handles UDP's unreliability through features like fragmentation and retransmission, all while presenting the core security of TLS. That's the main idea basically behind this protocol. Okay, now let's talk in more detail. So RFC 9147 highlights how DTLS can be abused in 2 major ways. First, attackers can trigger resource exhaustion by flooding servers with client hello messages, each demanding costly cryptographic operations. Second, they can launch amplification attacks by spoofing IPs, causing large certificate responses to be sent to victims, overwhelming them with traffic. Now something very interesting, in my opinion. So to counter handshake-based DOS attacks, DTLS uses a stateless cookie mechanism. The server avoids heavy computation until the client proves it's reachable by echoing back a valid cookie. This simple step blocks spoofed requests and prevents basically attackers from overwhelming the server with handshake attempts. While it seems a very solid attempt how to mitigate this attack vector, unfortunately, it's still far from perfection. So while the stateless cookie mechanism seems effective against spoofed IPs, it has a key limitation. It can't stop attackers using valid IP addresses. If the attacker can legitimately receive and resend cookies, they can still flood the server with handshake requests and trigger resource exhaustion. Now let's take a look at 3 examples. So example number 1. This capture shows a clear DTLS handshake abuse pattern. Dozens of client hello messages coming from the same IP address, in this case, the one hosted in the Netherlands. This capture, though, shows a clear DTLS handshake abuse pattern, but this time linked to a known scanning service census. So it's basically the same network traffic, however, coming from a different IP address. The abuse pattern is exactly the same, just showing you guys that we can expect such kind of traffic from, how to say, IP addresses that could be a different, could be basically indicating a different kind of risk. And our final example, in this very case, as you can see, the IP address has basically no negative reputation. So if we don't look deep into the packets, we could actually not be able to detect that it could be malicious traffic. Also, this proves my point that I have throughout my career have always been telling to everybody that it's important not to make decisions in SOC teams based on just IP addresses reputation. Anyway, in this example, we can see a high volume of client hello messages. Despite the no abuse listing, as I said before, the repeated handshakes still suggest a silent resource exhaustion. Okay, so now let's move to QUIC, a modern transport protocol built by Google, now standardized by ICTHP. Unlike traditional protocols, QUIC combines transport and encryption in one layer, running entirely over UDP. This eliminates round trips during handshake, drastically cutting latency. Thanks to built-in multiplexing, QUIC avoids head-of-line blocking, a big win over TCP. It's more and more common these days, I would say. Anyway, QUIC runs over UDP, which makes it faster and more flexible than TCP's connection-oriented model. Second, encryption is built right in. QUIC uses TLS 1.3 internally. Unlike TCP, where encryption is a separate layer. QUIC also supports the so-called zero RTT for lightning-fast connections and handles packet loss more efficiently without slowing down. One major highlight is connection migration. QUIC lets users switch from Wi-Fi to mobile data without dropping the session, something TCP obviously can't do. GQUIC, or Google's original QUIC, was an experimental protocol with its own proprietary handshake. Messages like chlow and shlow. However, ICTHP QUIC is now the official version, integrating TLS 1.3 for stronger encryption and better security practices. It eliminates those legacy handshake messages, which is very important. Today, ICTHP QUIC powers HTTP 3 and is used by browsers and CDNs, while GQUIC is considered outdated and should no longer be used. The initial handshake step in GQUIC can be exploited for denial of service attacks. While chlow itself isn't flawed, it's expensive to process. And this is the key again. Attackers take advantage of this by repeated chlow messages, often with the same connection ID, CID, forcing the server to use CPU and memory for each connection. This can lead to resource exhaustion, obviously. Chlow flooding was an effective attack in the early days of GQUIC, back in the day. Since GQUIC used UDP, which is stateless, attackers didn't need to complete a full connection. They could spoof chlow messages that the server still had to parse and respond to, and that parsing process was CPU intensive. Plus, early GQUIC lacked meaningful state validation, making it easy to overwhelm servers. Thankfully, these issues were addressed in ICTHP QUIC by introducing retry tokens and proper TLS authentication, which now make chlow-based flooding far less viable. This is a practical example of a chlow flood attack using GQUIC. The source IP is generating an overwhelming number of initial handshake packets, as you can see in this slide. They are directed at the same target IP with the same CID, connection ID, and the payload size is consistent. So basically, we can obviously very easily see the abuse pattern. Although ICTHP QUIC is a huge leap forward in terms of security and performance compared to TCP and GQUIC, it's not immune to layer 7 DoS attacks. The handshake process, even when streamlined with 0 RTT and 1 RTT, still involves costly operations, like, for example, elliptic curve Diffie-Hellman key exchange, certificate validation, and session state tracking. ICTHP QUIC fixes GQUIC statelessness and spoofing issues, but it doesn't eliminate the cost of handshake cryptographic operations. There is a tool called Quiche available on GitHub that provides a high-level API for sending and receiving HTTP requests and responses over the QUIC transport protocol. It can be used basically for DOS attacks if you wish for that. Okay, even though ICTHP QUIC is designed with strong security and performance improvements, research from December 2024, the one from which you can see some citations, still shows it remains vulnerable to layer 7 DoS attacks, especially handshake flooding. Recent work also proposes a fix, integrating crypto challenges directly into the retry token mechanism. This forces attackers to solve computational puzzles before the server commits resources. It's a very interesting idea. It should be given a try, basically, if you ask me. But it still shows what I try to make you guys realize, that these protocols need constant improvements, because the initial designs and then other designs one by one still have some issues. Okay, so now the last protocol, probably the most common one. Before TLS 1.3, earlier version of TLS had several architectural weaknesses that made them targets for DOS attacks. A handshake process required multiple round trips, which not only added latency, but also made it easier to exploit through repeated renegotiation or negotiation. TLS 1.2 brought major flexibility and quite a few improvements. I will not touch upon TLS 1.0, 1.1, because they are very out of date now. TLS 1.2 is still commonly used though. Anyway, however, renegotiation and downgrade vulnerabilities still lingered for TLS 1.2, depending on how the server and client were configured, which is very important. I mean, basically the configuration. Overall, TLS 1.0 to 1.2 laid the groundwork, but retained handshake complexity and vulnerability exposure until TLS 1.3 reconstructed things, resolving the issues to some extent, but again, unfortunately, not fully. This slide shows two renegotiation vulnerabilities. The first one, the main one, so the CVE 2011-1473 affected OpenSSL before version 0.9.8L. Attackers could trigger many negotiations in a single connection. This caused high CPU usage and potential DOS. What is very important in this context is that feasibility depends on configuration, software version, and if client renegotiation is allowed. It's very important that it would be enabled only in this very case the vulnerability exists. Okay, so the THCSSL attack exploits TLS renegotiation by repeatedly sending push-ACK packets over a single TCP connection, causing the server to perform costly key exchanges. This allows even a single attacker to exhaust CPU and session table resources without opening new connections. The vulnerability exists only when a server allows client initiation to renegotiation. This is what I said basically before. Just want to emphasize so that you guys know that this is the only reason why the vulnerability will be still in place. So TLS 1.3 improves security and performance by completely removing renegotiation, eliminating a major DOS attack vector. This was very impressive back in the day. It solved a lot of issues. It introduces perfect forward secrecy as a simplified handshake process to reduce server workload. These changes make TLS 1.3 more resilient to layer 7 attacks than earlier versions. However, unfortunately, as I said before, TLS 1.3 still remains vulnerable to concurrent handshake flooding, where attackers overwhelm the server by initiating many full TLS 1.3 sessions, exhausting CPU and memory. These concurrent handshake floods repeatedly trigger CPU-heavy key renegotiation, key generation, my apologies, and cipher negotiation, and also create memory-consuming session states, even without completing data transfer. Legitimate TLS clients like Firefox use many extensions to ensure capability with web services. In contrast, DOS tools often send minimal or customized client hello messages that lack typical extensions like SNE which is server name indication. These differences can help identify abnormal TLS traffic. Legitimate TLS clients use varied extension headers based on their OS, browser, or version. Malicious traffic often reuses identical minimal client hello messages, making it easier to detect due to its repetitive pattern. For example, the presence of a signed certificate timestamp extension can help distinguish Chrome for Firefox. Even though this traffic is obviously encrypted, we can still draw a lot of conclusions based on the knowledge one could have. This captured network dump shows a series of client hello messages sent in rapid succession, a pattern that is a key indicator of DoS activity. Obviously affecting the CPU and memory, if conducted properly. Okay, so this diagram though shows how a TLS DOS attack works by overwhelming the server with handshake requests, consuming its resources. It's basically a realization of how it's done. TLS DOS attacks using some Kali Linux tools, like for example the very one in the slide, which is THC SSL DOS tool, cannot succeed when renegotiation is disabled. Hence, you can see quite a few errors, times out messages on the right-hand side in this slide. TLS DOS attacks can still succeed using OpenSSL tool, even when renegotiation is disabled. It doesn't matter. To demonstrate this, we can see many established connections in the terminal screenshot on the right-hand side. You can see the connected messages. We'll conduct a TLS DOS attack using OpenSSL to demonstrate its practical impact at the end of this webinar. Anyone can do this with just a laptop, which is pretty scary, to be honest. And many machines are needed to cause significant disruption, but still this proves my point that all these protocols are vulnerable to this. This demonstration uses TLS 1.3 to perform a practical DOS test against a target server. TLS 1.3 is the supported version, which we can deduce from the responses from the web server. As you can see, quite a few packets, starting with packet number 37 towards packet number 55. You can see some client hello requests and then responses from the servers, and based on the comparison, you can come to the conclusion that TLS 1.3 is the supported mechanism for this web server, which in this very case is my official website, michalsołtysik.com. One terminal window runs a TLS DOS attack using a custom OpenSSL-based script. The second shows the current number of established connections, while the third displays live server overload by comparing baseline RTT with current RTT. The attack is conducted against my official website, the one I mentioned before. Two of these terminal windows are output from Python scripts run in the operating system. So basically, in order to conduct this attack, we just need OpenSSL and Python, Kali Linux box, and probably that's it. Plus access to the internet, obviously. Okay, so this TLS DOS attack increases CPU usage, inflates RTT delay, and pushes the server toward saturation, with OpenSSL connections stressed in Michał Sołtysik. Mind you, that both the attacker and the server can influence RTT due to CPU usage, network congestion, network interface controller queue saturation, handshake complexity. So basically, both ends are responsible for the delays. To sum up, each protocol mentioned in this webinar was shown to suffer from 1, handshake abuse, very critical, 2, packet fragmentation, and 3, amplification risks. This is the summary for ICP, QUIC, and QUIC. This was covered before. just a summary. This is the summary for WTLS and DTLS. I also covered this before, but still for you guys in separate slides for you to have access to later on once we publish the webinar online. To sum up, TLS 1.3 remains vulnerable to full handshake flooding. I want to emphasize this fact. This consumes CPU and memory due to its cryptographic complexity. Okay, so let's now talk about conclusions. Layer 7 DOS attacks exploit weaknesses like 1. Packet fragmentation, 2. UDP-based protocol limitations, and 3. Cryptographic handshake complexity, which is very critical. Even modern protocols like TLS 1.3 and QUIC, the last version, remain vulnerable to resource exhaustion when handshake processes are abused at scale. Probably something around 100,000 per second, I think at least, but still it's possible if we have enough resources and motivation probably. Okay, so what would be the final conclusion? That we need like a solution, right? Always when you have a problem, we need a solution. So I just came up with a few theoretical solutions that could help to create and design a protocol that would be much more secure for us, for everybody, for all the web servers. So to prevent layer 7 DOS attacks, future protocol must, for example, 1. Delay state tracking until client verification. 2. Reduce handshake complexity. Handshake is always a problem. 3. Verify clients early without exposing resources. And 4. Allocate resources dynamically to handle traffic spikes. To defend against session exhaustion and handshake flooding, protocols should, for example, use stateless validation and lightweight, efficient handshake mechanism. To strengthen layer 7 DOS defenses, protocols should, for example, verify clients early before encryption and throttle resource allocation dynamically based on real-time traffic conditions. Before we go to the Q&A session, because we still have 5 minutes, I see, I would like 8 minutes. I would like to present you how to conduct such an attack live using a Kali Linux box. Hopefully I will make it in time. What was the... Okay, here we go. Okay, so as you can see, we'll be conducting this attack against my official webpage, which is michałsołtysik.com. It should be online. It is online. Anyway. Here we go. It is up and running. As you can see, this is the IP address of the website. Okay, so first of all, we need to check what the RTT baseline is. So how usually without the attack taking place, the server is responsive. So we'll do that by establishing the RTT baseline using 50 packets, and the average would be the baseline. At the same time, we'll be checking on number of established connections sent from this attacking machine to our victim server. However, as I said before, the delay will be affected also because this machine will be basically overwhelmed by the attack. So for this very reason, we'll be also checking the RTT from another machine, not the virtual machine that is used for the attack itself, but also on my local machine. Okay, we still have 5 minutes, it should be enough. As you can see, the baseline was basically measured in my attacking machine, and there's 15 seconds remaining before the baseline will be compared to the current RTT values. 5, 4, 3, 2, 1. And now, as you can see, we'll see the status, meaning the difference between the baseline and the current situation. Okay, now we have to wait 34 seconds till we have the same situation in this machine. So let's wait half a minute. $20 seconds. As you can see, mostly the overload is either very, very low or it's normal, so there's no overload detected, which is obvious because nobody's attacking the server yet. Okay, 5 seconds remaining. 3, 2, 1. Okay, let's minimize. Okay, now as you can see, everything's ready. We see 0 established connections from this attacking machine towards my official web page. Now we'll start the attack in the third terminal window. Enter was hit. A lot of traffic is being generated now. Let's give it a second. As you can see, we already have 64 established connections, 153 established connections. Of course, this will take a lot of time. It will be trying the machine to do increasingly solid work for me. And it's just one laptop, which is not a strong one when it comes to its processing power. But if we, for example, use 100 such machines with just a very simple setup like the one you see now, you can achieve great impact. Anyway, as you can see on the left-hand side, the overload is at 20% more or less now, which is not fully accurate actually, because now, as you can see, it's at 7 more objectively, because this terminal window is not affected by the CPU being overloaded because of all this traffic being generated from the attacking machine. Anyway, just to show you guys that you can do this very easily with just Python, with just OpenSSL, with a simple box. Everybody can do this because these protocols, unfortunately, are not perfect. They're far from perfection. Even the latest designs, the latest version, something that was redesigned multiple times by very smart people. Anyway, we can go on and continue this attack, as you can see in my Kali Linux box now, and it will actually get worse and worse and worse with time. And if I do this with more than just one laptop, you can see even more impact. Okay, and last few minutes, want to show you something in Wireshark. So in order for attacker to see if your server is vulnerable, it's very easy just to use one command, and then as you can see that, for example, the web server in this example, in this case my official website michałsołtysik.com, support TLS 1.3, but it's not a problem whatsoever, even though it's supposed to be the latest achievement in the world these days. When you want to see legitimate traffic, so not the one I'm generating now from my Kali Linux box, you can see that there's the extension, server name indication extension, which might prove that, and mostly in most cases it proves that this is legitimate traffic generated by a human on purpose, without malicious purposes in mind. However, such packets will look completely different if you're using malicious tools like the one I'm using right now. So when you go to the third network dump, guys, you can see that there's no extension like SNE in the client hello packets once you're using such tools for the attacks, because it doesn't matter. As long as you just send the request that will do their work, you don't need all these extensions that are being supported by some browsers. These are just small differences in the packets, but as you can see, based on enough knowledge, you can actually see in the network dumps what was the reason behind generating some kind of network traffic. Okay, so this is it. Thank you so much, everybody, for your attention. Hopefully you enjoyed my session, and I'm open for Q&A now. Thank you again.
Thank you very much, Michał, for delivering such an insightful and informative session. We found the webinar very engaging and hope it was valuable for you as well. Now, before we begin with the Q&A part, I would like to inform all the attendees that EC Council CND map to many roles in the industry like Network Security Engineer, Network Security Administrator, Network Security Analyst, Network Security Architect, Network Defense Technician, Security Operator, etc. Anyone with a CND certification is eligible for 135,000 plus job vacancies globally with an average salary of $85,613 per annum. If you're interested to know more, kindly take part in the poll that's going to be conducted now. Let us know your preferred mode of training and we will reach out to you soon. So, Michał, shall we start with the Q&A?
Sure, yes, please go ahead.
Thank you. So our first question to you is, how can one break the chain of TLS and SSL encryption? Is there any way to view data in plain text format? How do attackers intercept encrypted communications?
Yes, it can be done. Of course, it's heavy processing. So you would, for example, need to have enough hardware, or basically you just need to be prepared so that you can do the job, but it's possible. Of course, in order to explain this in more detail, I would need much more than just 2 minutes, because it will depend on a lot of factors. You need to be also, so to say, between client and server. There's a lot of things that need to be kind of happening so that this is actually at all possible. But yes, it is possible also for actually non-malicious reasons. We can also be done. We have a lot of decrypting solutions. But anyway, if somebody wants more details into this aspect, this topic, then please feel free to email me, and I will give you a much longer and solid explanation. My email address is me@michałsołtysik.com. Thank you.
Thank you for answering that question. Our next question to you is, can you provide guidance on advanced steps for packet analysis, such as using open source tools?
Yes, of course, but again, I think that if you have very specific questions, you can email them to me, and I will be very happy to answer them, because this is a very general question. guidelines. There's a lot of network security, network forensics courses online in the internet that you can get knowledge from. For example, C&D from EC Council, WCNA, so completely devoted to Wireshark, #1 tool for the packet inspection, obviously. And there's a lot of actually online free material, like on YouTube. You can also Google me, just search for Michał Sołtysik in YouTube, and you can see a lot of content from me. Also, when you go to michalsołtysik.com, when you go to one of the tabs, you will see some cybersecurity content. You can also get some knowledge from that place. Basically, now we are in 21st century. Everybody's online, so I don't think it's an issue to get any knowledge about this. But again, yet again, if you have any very specific questions, feel free to email me. Thank you.
Thank you for answering that question. Michał, can you please switch to the thank you page?
Yeah, sure. My apologies. I forgot doing that right now.
Thank you. Thank you. Our next question to you is, does Google still uses QUIC?
It's not that common these days. I agree. However, if you do what I do, which is network edge profiling, you will see that they are trying everything, literally like every page in the book, so to say. They're trying all the exploits, things that might not necessarily even work. It's like 0 days, like old vulnerabilities, everything. We are using everything to go through, if you know what I mean. I saw what you could see in one of the slides, this QUIC flood. I think it was like a year and a half ago, something like that, not a long time ago. QUIC obviously was designed much earlier. Anyway, it's still being generated by some malicious public IP addresses. But yes, I agree, it's not going to be common these days, but it doesn't matter because, I mean, this knowledge is still, I think, important. The more you know, the better you will be at detecting threats, and that's probably the reason why you are in this industry, right? To be a SOC analyst or somebody like this, so that you can help to mitigate threats, to detect threats, and so on and so forth. So the more you know, the better for you and the company you work for or at. So yeah, that's I would like to answer this question. Thank you.
Thank you for answering that question. Our next question to you is, what is the name of attack that you had showed in the demo?
That's a TLS 1.3 full handshake flooding. I basically used, as I said before, I used the OpenSSL tool. I basically wrote a script using this tool, and this script was sending out parallel, aka concurrent, TLS session requests to the vulnerable web server, even though it was supporting TLS 1.3. A lot of concurrent sessions were being sent from point A to point B to the target IP, and basically the server was kind of, so to say, feeling as if hundreds of people were trying to access the website, even though it was obviously not true. So as I said before, if we use more laptops, not just one I was using now, then we can unfortunately make the web page perform much slower or even go down for some time. Thank you.
Thank you for answering that question. We'll take last 2 questions for the day. Our next question to you is, what is the status of using machine learning or deep learning models for the detection of layer 7 DoS attacks?
It's a good idea. I think it could be done. It depends on what solution you want to opt for. Basically, machine learning is being used, I think, these days in SIEM solutions. However, in SIEM solutions, it's difficult to detect some attacks if they're very complex, if you know what I mean. But anyway, machine learning is a good example. There's a good course out there certified cybersecurity consultant, highly recommended. It includes a lot of information about machine learning in terms of cybersecurity. So you can see a lot of different examples with different attack vectors, how to use machine learning in the cybersecurity industry. But yeah, like once I said again, it really hinges upon a solution you want to use. If it's it can be done, how it can be done is also not that easy, to be honest. So it really requires a lot of additional questions before I could easily answer the one you asked. So it's something, a good idea, but something that would require a long discussion to answer this question fully. I hope you know what I mean. Thank you.
Thank you for answering that question. Our last question to you is, what tools can be used to detect illegitimate TLS traffic?
Before I answer this question, I want just to emphasize that these questions show that people who ask them are knowledgeable. I'm very happy to see that, but these are very intelligent questions. I'm very positively surprised. Oh, okay, so let's focus on the last question. How to detect malicious TLS traffic. I'll just give you one example, a real-world example from like 2 or 3 years ago at my current workplace. When I was I was successful in detecting a TLS DoS attack against an official website of one of our clients. So basically, I did not use any solutions like top solutions like Gigamon, Archime, and so on and so forth. I was just browsing network traffic in a SIEM-alike solution. I just saw that there were a lot of different IP addresses, obviously, sending traffic towards a destination IP, which was the web page I was focusing on. But I saw an abnormal amount of packets being sent from one IP address. Of course, it doesn't have to be one IP address. It can be a network. It can be even higher in the topology. But anyway, I saw just one IP address being there in the logs too often, if you know what I mean. So I was suspicious because it was abnormal. So then I went to the firewall and I sniffed the traffic. I sniffed the traffic and then did the deep packet inspection analysis of this TLS network dump. And I did see some abnormal elements in the network dump, in the especially client hello packets, as I explained today in this webinar. You can see some differences. So if you just study hard TLS, you will know exactly how the standard traffic looks, depending on various versions and so on and so forth. But if you have enough knowledge, you will see and you will notice the differences. And based on these things that you might notice, you will come to the conclusion that this is an attack. And you will not have to rely on a reputation of an IP address, for example, because you can have more solid foundations that will make you, for example, block this IP address. Anyway, there are a lot of ways how to detect such attacks, depending mostly on the system or systems, hopefully, the one you can use, you have at hand, right? Because you're probably working at a company, they probably either have a SOC outsourced or in-built SOC, built-in SOC, but so the scenario for you or somebody else might be completely different. So it's difficult to answer this question just one way because it really, really depends. Anyway, if you have enough knowledge, you have some, how to say, solid team around you and some solutions in place, then with constructive thinking, you can easily get the job done. Thank you.
Thank you so much, Michelle, for the message to. Thank you again to our wonderful speaker, Michelle, for answering those questions and for the great presentation and knowledge shared with our global audiences. It was a pleasure to have you with us, and we are looking for more and more sessions with you.